So guys, I was having a look at the data that is with us, and it's kind of lining up in this box and it's not coming off the box. So it kind of got me start wondering why the doubling rate is the number of days required for the cases doubling increasing in although it's on the same graph. So I thought I should have a relook at the model. So just to revise, if you remember, I had this, which is the new cases is equal to some magnification factor and directly proportional to the total number of cases. So when you integrate this out, you get this kind of an equation where you get the exponential growth, and this is the magnification factor. Now, what I changed here is I make dy by dt is now equal to k y raised to n. Okay, now the advantage I get with this is by varying m, that is, say if I make m is equal to 1, I get this equation. If m is equal to 0, I get this equation, k y0, which is k1, which is k, which is linear growth. And if m is less than 1 and say is negative essentially, and becomes very very large and goes to negative infinity, you get dy by dt is equal to k y raised to negative infinity, which is k0 is equal to 0, which is no growth. So basically what to describe what I'm doing exactly, say this is a big graph. Okay, I'm going to put some markings on this. Say this is the linear, okay, and say this is the exponential. Okay, so as this is also m is equal to 1. Now as the cases keep on growing, let me put another mark so that I can guide myself on this video. So now if m is greater than 1, basically you get this kind of a case. Okay, now as m goes to positive infinity, you would have this go shoot up like this along this line. Okay, now m goes to 1, you get your exponential. But now here's the interesting cases. So when m is less than 1 but greater than 0, you get this kind of a case. Okay, and you can see that if you keep on reducing m and you make it 0, you get the linear graph. And now once you start making it negative, you kind of start getting this kind of a graph. That means you can see the flattening coming in, which they say curve flattening, to the point where say m increases to negative infinity, then the graph will move straight like this, and you will get the curve completely flattened. So by varying m from positive infinity to negative infinity, I can get all these variations. Now it's important to note that m is equal to 1 is how the virus naturally grows. So one cell becomes 2 cells, 2 cells become 4 cells. So it will always grow along m equal to 1 shape. Okay, so these graphs are not going to be possible. What's going to be possible is m less than 1 and greater than 0, which is what we are getting. Then m equal to 0, which is linear, and then n becoming negative, which indicates curve flattening. Also, basically how far m is from 1. Okay, how far m is from 1. So say m is 0.9, or in some cases m is 0.8, will represent how much social distancing or lockdown or population density is affecting the curve. So m equal to 1 is the ideal case of exponential growth. Anything less than that is what is affecting the curve. So because of lockdown and this, and it is making the curve either linear or flattening the curve, or it is completely stopping the growth. Okay, so going back to this set of equations, this is our main equation, and what I'm going to do is I'm going to do a log on both sides. So I'm going to have ln dy by dt is equal to ln kym, which is equal to ln k plus ln ym is equal to ln k plus m ln y. So let me just rewrite this as m ln y plus ln k, and here is ln dy by dt. Now I'm going to plot this versus this. Okay, and we're gonna observe how that works out. Basically, this versus this, you're essentially gonna get some plot like this, which is a straight line first, having m, which is this greater than 0 but less than 1, then like this, which is m equal to 0, and then this showing negative decline, so this is m negative. Okay, if you remember, most of my data you'll find goes like this, then has some flattening, and then there's a big decline. For my all countries plot, it was like this. So this is that plot. This plot is of ln dy by dt divided by the population of the country, scaled by the population of country, versus ln y by y0. Again, y0 is the population of the country, and you can see it's a fairly straight line. And when you find out the slope of that, so in this case, in India's case, this is m, it's about 0.8. So think about it this way, that 0.8 is our social distancing or lockdown factor. Ideally this should have been 1. 1 would indicate perfectly ideally how the virus is growing, but since it is less than 1, it's about 0.8. that is how much we are able to change the curve. Also, this represents the magnification factor. Okay, and again, this magnification factor is also affected by the lockdown. So better the lockdown, better the social distancing, this one will be closer to 0, and this one will be slower. At the same time, if this, what our aim is to push and make this 0. As you can see, this is at 0.81. Even at the current stage, we are at 0.81. So you can see that this is far away from 0, and we are nowhere near coming to curve flattening. Okay, because this is still far close to 1, then it is far close to 0. All right. Now coming to the doubling effect. Okay, so for that, what you need to do is we have to resolve this equation, that is dy by dt is equal to kym. So to integrate this is dy by ym is equal to k dt. Integrating this, you will get 1 minus m upon y raised to 1 minus m upon 1 minus m is equal to k t plus an integration constant. Now this is kind of difficult to evaluate in this case, so what we do is we do a 2-point difference system. So say at point 1, this is y1 is 1 minus m is equal to k t1 plus c, and y2 1 minus m upon 1 minus m is equal to k2 plus c. Now you take the difference of these 2 points, so you will get y2 1 minus m upon 1 minus m is equal to minus y1 1 minus m upon 1 minus m is equal to k times t2 minus t1, and basically the c cancels out. Then you take then you want to see the doubling rate, so we say that y2 is equal to 2 times y1. That will give us the doubling rate. So this is 2 y1 is to 1 minus m minus y1 is to 1 minus m divided by 1 minus m is equal to k t2 minus t1. So taking out y1 this common, so this will work out to 1 minus m minus 1 upon k 1 minus m is equal to t2 minus t1. Okay, this is the final result. And just to compare it to how it was what it was doing in exponential, so say y1 is equal to y0 exponential kt1, and y2 is equal to y0 kt2. Now you take, in this case you have to take a direct ratio is equal to e k t2 minus t1. Now this is doubling, so basically you have 2 is equal to e k t2 minus t1. Taking log on both sides, you get ln2 divided by k is equal to t2 minus t1. Okay, so you can see the difference in t2 minus t1, and the main difference is this is not dependent on the total number of cases, whereas this formula is dependent on the total number of cases you have. Okay, so basically as the number of cases are going to grow, the doubling rate is also going to increase. Okay, so the doubling rate, the number of days, is going to increase. Similarly here, the doubling rate is not going to increase with y. It is just going to stay constant because k is a constant, but in this case it's going to increase, which is why we are constantly seeing the doubling rate increase. And just last bit of what I did is I compared the actual data of doubling rate to what I got from this model. So say 1000 cases becoming 2000, 4000, 8000, 16, 32, 64 and 1,28,000 for India. Setting at 1000, say it's 0 days. So for 1000 to become 2000, it took us 4 days, but the model gave me 7 days. Okay, this was a little away from the prediction, but you can see as the numbers go higher, so 2000 becomes 4000, 8000, the days are actually kind of matching up. 11, 64 is 13, and 1,28,000 is about 14 days, worked out to 14 days, actually happened in 13 days. And if you see, this kind of lines up with this graph and this peak here. So 1000 becoming 2000 happened really rapidly, which was higher than the data set of the graph, and that is why this data point doesn't match. Okay, the rest of them match up pretty well. All right, thanks, bye.